This
No, it's the sort of thing that the astrobiologists are really excited to look for.
yeah,
And now the question is, uh, okay, we have now found one of those a chemical which is on your list of things that might be a sign of life. Now what do we do? Where do we go with that?
yeah,
And suddenly Venus has gotten a lot more interesting.
yeah. And why aren't we getting phosphosulfides? That would be the logical end to the phosphine. And of course, that would precipitate immediately. That drops down right to the surface. So what's going on in the surface chemistries as well would be very interesting to see.
Yeah, well, at 800 Kelvin, maybe something interesting does happen.
Yeah, something weird is going on. I mean, we got boiling, and my machine just froze.
Yeah, I can hear you, but your picture froze.
Yeah, same.
Uh-oh.
Like the
Am I back yet? Yeah, it did.
Yes.
It goes out to lunch every once in a while, and I don't know why, but
So naughty and so complex.
well, welcome back, Scott.
Yeah, we got the YouTube audio working. So Dave said there are some people watching us on YouTube. So we're ready to go.
So we've been discussing phosphine,
Oh yeah, the Venus phosphine issue, huh?
and we've come to the conclusion that we have no idea what's going on.
All right.
And that's the most fun conclusion in science,
Yes,
actually.
it is.
But they also came to the conclusion that they want to know more.
Yep.
Yeah.
Well, what about have you considered the possibility that it's magic?
Well, what's magic? As Arthur Clarke says, magic is just technology you don't yet understand.
I like that. Yeah, that's true.
But I think the technology on Venus is vanishingly small.
Well, okay, fine.
Yeah.
But in this case, it's some natural phenomenon that we don't understand. I mean, if it were to turn out to be something that we could reproduce, we would cease to think it magic. And if
Yeah.
it wasn't something we could reproduce, we'd have real trouble even classifying it. I mean, there are odd things happening all the time. We still don't really understand supernova 1998 BW, which seems to have been associated with a gamma ray burst, but on the other hand, its luminosity makes no sense.
Oh.
So
it was a misbehaved supernova?
well, it was a peculiar supernova of the type that we think is associated with gamma ray bursts. But it was relatively close to us. But the gamma ray burst that accompanied it, that seems to have accompanied it, looked like it was at cosmological distance. It was much fainter than you would expect for a gamma ray burst from a supernova as close. I mean, I forget how far it was. It was,
It seemed
hundreds of megaparsecs, but it was not gigaparsecs. Okay, it was, in gamma ray bursts, the idea of close needs recalibration. Now we have seen another one that was even closer, and that was extremely, and it looked, it was a similar peculiar supernova, but the gamma ray burst associated with it was extremely bright. Yeah, it was GRBO 30329, the brightest burst that my HEDI 2 mission found. And that one fit the, what we know about gamma ray bursts. But this other one, if the supernova was associated with the gamma ray burst and it was awfully close in the sky.
You're talking about 1987A, right?
Yeah, well, 1987A didn't make a gamma ray burst.
Oh, okay. So this is a different
1987A was a different sort of peculiar supernova.
Okay. So this is 1987A is the one people probably have seen a lot of news stories about over the decades. That's the one that happened in the Large Magellanic Cloud. So the one you're talking about, the one that had an anomalously weak gamma ray burst, that one was also close, cosmologically speaking. Close.
It was a lot farther than the 1987A, but cosmologically speaking, it was close.
Okay.
And therefore, the gamma ray burst should have been bright, and it wasn't. And now it's like, okay, I mean, our first inclination was, okay, this is evidence for a whole population of fainter gamma ray bursts. But then we went and looked real hard for them, and we didn't find them. So, you know, that one is still one that got away. Another crazy example is Bloch Cabrera's magnetic monopole. Remember that?
Well, I know that there have been, what I do know is that there are magnetic monopole searches that have been underway for decades, and none of them have come up with any good evidence yet.
Well, no, Cabrera got one.
Oh, okay.
And it looked really good. But nobody believes it anymore because he then did a search that was 100 times more sensitive and found none. Yeah.
Fascinating.
No one has found any flaw in his experimental result. He is renowned as a careful experimenter, and yet he got this one weird anomalous result that looked precisely like what you would expect for a monopole, and then couldn't reproduce it. Nobody else could either.
Is there any notion about whether the signal was consistent with something that had a cosmological origin, or was it just like a terrestrial,
he just had a magnetic loop, and superconducting magnetic loop, and he was monitoring the current in it, and if a monopole went through it, there was a certain increase in current expected. There's a quantum mechanical argument due to Dirac that tells you what the elementary monopole charge should be. Okay. And he saw a sudden increase in current in his superconducting loop that matched the prediction. And in the whole course of the experiment, he didn't see any other signals that were anything like that. It didn't fit. Yeah, when he was pouring more helium into the dewar, he would see a little bit of noise. But this was a much larger signal than anything that any known interference source would produce, and it exactly matched the signature of a magnetic monopole. This was about 40 years ago now. It was quite a long time. Yeah. It's a mystery.
So there are cosmic mysteries out there. Speaking of mysteries, one of them that sort of hit the news in the past couple of weeks is a new survey of gravitational lensing due to dark matter, and has caused some head scratching. Do any of you have you read that story? Do you have an opinion or insight into that?
Well, I read the story. I haven't read the papers. Dark matter is tricky stuff. We don't know what it is. And so we have guesses, we have guesses as to how it should behave. But this is suggesting that our guesses are not quite right.
Well, even worse, it's a long way off, if I understand the paper correctly. It's not that we missed it by a little bit, we missed it by a lot.
Yeah, I think that the new survey done by Hubble and some other telescopes look at gravitational lensing. So for those viewers who aren't familiar with the idea, this is the mechanism by which Einstein became famous. So gravitational fields correspond to a bending of space and time, a warping of the geometry. Otherwise, the naive assumption is that we live in a universe that's flat. We can apply Euclidean rules that right angles are always perpendicular, and that parallel lines never meet, etc. But Einstein's theory of general relativity related the effects of gravity to a geometric change in the metric, or the definition, the defining characteristics of the geometry of spacetime. And one of the implications of that is that things that make large gravitational fields, like our sun, our sun actually makes a modest gravitational field compared to a galaxy or a black hole, but that kind of gravitational source will actually ensure that light rays skimming across the surface of the sun will be bent a little bit by from our perspective, because of the geometry change. And the way that they saw that was during a total eclipse of the sun, when they could see the light rays of distant stars, and the images of those stars were deflected a little bit. So this gravitational lensing, where gravity sources bend the paths of light rays, has become a very important tool for astrophysicists to probe the gravitational distribution of matter in the universe. Because as far as anyone knows, and as far as general relativity says, the only thing that can create gravity is stress within matter, or a clump of matter, or energy. And matter and energy in some sense are kind of indistinguishable. We might get into that later. So anyway, these gravity wave surveys look at cosmological scales for the lensing effects of galaxies and clusters of galaxies, or individual things like an individual neutron star and whatnot. And this most recent survey looked at a galaxy cluster, so thousands or millions of galaxies in a relatively, this is all relatively speaking, compact area of the universe, or space-time. And they found that within those, the individual deflections of light rays around galaxies was, if I'm remembering correctly, anomalously high. So instead of the dark matter being distributed fairly evenly throughout the cluster, it seems like it's a little clumpier than some of the theories predicted. There's no good theoretical explanation for why that might be the case now.
Yes, our understanding of why ordinary matter clumps much more than dark matter does is that ordinary matter can emit light, and therefore when you bring together a bunch of gas and it collapses and heats up, it can get rid of that energy that of the collapse by radiating it away as light, and that allows it to collapse further. And our current models of dark matter are that it has no dissipation mechanisms like that at all, and that suggests a certain amount of clumpiness that takes supercomputers to simulate and all that. So let's take.
It's a modest amount of clumpiness, right? It doesn't.
It's modest. It's modest, but right. Let's also note that it takes heavy duty modeling to figure this out, and let's now. I'm sure what's happening is that the modelers are going back and looking at how their models actually function. But suppose dark matter has some mechanism for radiating away its energy. Suppose there is, people talk about shadow matter, which has its own fields that it interacts with, and might have an analogous thing to an electromagnetic field that would allow it to radiate away extra energy. It's really hard to probe this. The problem that we have in theory is that there's absolutely no fundamental reason that we should expect that every kind of particle and field will interact with our instruments through anything but gravity. So we know about the ordinary matter that makes up our universe because it's the stuff that interacts with the instruments that we use. We know about electromagnetic radiation because it's the stuff that interacts with the instruments we use. But almost all the matter and energy in the universe is something else that doesn't interact with our instruments. But maybe it interacts with, maybe it's more complicated than just a simple gas of non-interacting particles. Maybe that there are more interactions going on. Wouldn't be at all surprising.
Yeah, what's that called? Is it called the dark realm or the dark?
I've heard it called shadow matter. There probably are more terms.
Yeah, there are speculations that dark matter might interact via the weak nuclear force and gravity, and that's it. Well, both of those forces are weak. Gravity is actually weaker than the weak nuclear force, but the weak nuclear force is so feeble that it's incredibly difficult to measure phenomena that result primarily or for practical purposes only from the weak nuclear force. One great example of that is neutrinos. Neutrinos don't have an electromagnetic charge. They do have an incredibly feeble mass, but the mass is so feeble that no experiment accessible to modern science can measure their gravity, for example. So the only thing we can really do with neutrinos is measure their interaction with matter that arises because of the weak nuclear force, which is feeble enough that a neutrino could go through something like a light year of solid lead before it has a 50% chance of interacting with one of the atomic particles in that block of lead. So there's a lot of speculation that dark matter may also interact via this weak nuclear force. And so a lot of the experiments that have been created and theories that have been constructed to search for dark matter are predicated on this assumption. And as far as I know, every single one of these experiments has come up blank. There's been no evidence.
Well, the problem is it's an assumption.
Yeah.
But it's the only assumption that you can make based on a known force that has the potential of allowing you to detect dark matter. Because we know it can't have electric charge because it's dark. If it interacted with electromagnetic radiation, we would have found it. That would make it very easy. We know it doesn't interact by the strong nuclear force because it doesn't interact with nuclei and things like. Again, if it did, we would have found it by now. So the weak force is the only thing left that we know. But that's like the old story of the drunk looking for his keys under the lamppost. Why are you looking for? Where did you lose your keys? Oh, I lost them over there. Why are you looking for them under the lamppost? Well, it's the only place I can see. Yeah.
Right.
And we really, the only thing we know about dark matter, everything we know about dark matter has to do with how it interacts gravitationally. And of course, it only interacts gravitationally in enormous quantities because the gravitational force, while it is weak for an individual particle, adds up. And there is an awful lot of mass in the dark matter in a galaxy, much more than there is in the stars. So we see the evidence of the dark matter in that gravity. That's basically the only handle we got on it. And of course, gravity's what's behind this gravitational lensing result. But now we have a measurement that suggests that it's not quite the completely perfect non-interacting gas of particles that our models assume. So, modelers get to go back to work.
So the two leading ideas for dark matter that I'm aware of, one is these weak force interacting particles. They're called WIMPs. Physicists have a history of coming up with colorful names, including some elementary particles have an actual color charge, speaking of colorful. But WIMPs is weakly interactive or interacting massive particle. The other scale side of the spectrum, instead of these very rarefied lightweight particles, the other notion is called machos. And those are massive, let's see, what's that? Now I'm going to forget what the acronym is. It's essentially
Big.
Compact halo objects.
Yeah, compact halo objects. So things like black holes or brown dwarfs or things that don't radiate. A black hole alone in space with no matter falling into it would also not emit any light. So there's some ideas that that a component of what we measure as dark matter may be these machos, massive ordinary matter that is not luminous for various reasons. But I think up until at least recently, a lot of those models have been ruled out because in most cases you'd see at least some infrared signatures or other.
Well, you'd see infrared from the brown dwarfs. You'd see gravitational lensing from the black holes if they had the sizes of the black holes we know about. Now, if they were the size, if they had if you have black holes the masses of small planets, that might work as a macho theory, but we don't understand a mechanism to create those.
Okay.
We think we understand how to make black holes of the masses of stars, and we now are seeing the cascade upward from the masses of stars into heavier things in the gravitational wave results. But we don't know how to make really small ones. And the other thing is it could be you just don't know the mass scale. It could be dirty socks. The only problem,
Cold
it could be, well, there, yeah, well, hot doesn't mean hot in the sense that the particle that whatever the objects are hot. It has to do. People talk about hot dark matter and cold dark matter, but that has to do with the velocity that things are moving around, and not necessarily the temperature of the objects if they possess temperatures that an isolated electron doesn't have a temperature to it. So.
Right.
An isolated dark matter particle might not either. On the other hand, if it is old dirty socks, they would have temperatures. But that's kind of ruled out by the fairly good understanding of nucleosynthesis. They would have to have come into being without the hydrogen and helium that they would have been synthesized from, and that doesn't work. But the point is that they could be reasonably massive objects, and they don't even need to be entirely opaque if they're reasonably massive objects, but they just can't clump very much.
Yeah, we know that, right? I mean, we know that they cannot be clumping.
But now we're learning that they probably clump more than we thought.
Right.
But yes, they don't clump like the matter that makes stars. The dark matter halo of our galaxy has not collapsed into a disk. The reason that the stars are mostly in a disk is because the gas that made the stars collapsed into a disk, and it collapsed into a disk by radiating away its excess energy as blobs of gas ran into each other. They got rid of their energy, and the low energy stable state, semi-stable state that they dropped into was a ring, was a plane, like Saturn's rings. Saturn's rings are another example of matter collapsing into a disk. And that's what matter tends to do around in a massive thing in space, is it tends to collapse into a disk. And the reason it can is because it has electromagnetic radiation, which is a way to get rid of the excess energy.
Right. Dave, our moderator, Dave, says that some people may be experiencing audio issues on YouTube. If so, you can use the YouTube live stream, I believe, to just type in a message, and you can let Dave, the moderator, know if you're experiencing any problems. You can also type into YouTube any questions you have, and Dave will relay those to us. Also on the YouTube is information about a website you can go to if you want to ask a question via voice or video. That'll forward you into a private Zoom meeting, and you'll be able to potentially ask a question there. So again, this is Sidewalk Science, and so far today we've been talking a lot about dark matter and the recent discovery of some unexpected clumpiness in the dark matter observed in a large galaxy cluster out in the universe. I'd like to switch gears a little bit, and I had a curiosity the other day, Abby, our physiologist and biology expert, and my curiosity was, why is it that we have evolved kneecaps but not elbow caps? Because I hit my elbow the other day and it hurt like a son of a gun. I don't know why they call it the humerus bone. And yeah, why are there kneecaps but not elbow caps? Do you have any insight into that?
Well, I can't say anything specific about that other than the fact that our bodies are not made to order, and that's the fundamental problem. That, if something happens to be there and that's useful to the body, that's real nice. But in terms of doing something, having something simply because it would be useful, not the way evolution works.
What about vestigial organs? Can you talk? Can you talk a little bit about that? You just make me think about that. Maybe we don't have things that we could benefit from, and then on the other hand, maybe we have things that are not needed anymore.
Yeah, I mean, what I like to say is that the fundamental bar that an evolved feature or system has to clear is good enough to not cause death before reproduction too much of the time, which is not a very high bar. And what this means is that in terms of vestigial organs, there are things that our ancestors may have had or used that were actually useful to them, that as we have evolved into our current state of being are no longer useful to us, but they stick around because they're not detrimental enough to cause death before reproduction too much of the time.
Wow, what a low bar.
It's a low bar, exactly. Now you understand. This explains many of your problems. So kind of a classic, easy example of a vestigial organ is, the hair on our arms and so on. Obviously, lots of animals are furry. Lots of mammals are furry. And most furry mammals benefit from the fur, usually because it keeps them warm. But we don't get real, warmth benefit from our hair, but it just hasn't gone away entirely because it doesn't really hurt us to have some hair. So we still do. But for instance, that is why, speaking of furry animals, that we may see a furry animal here in just a moment.
Oh, awesome.
Okay.
So yes, here we have an example of a furry mammal. But basically, sometimes your hair stands up on end. You've probably had that experience. You're cold or when you're frightened and the hair, it's not just an expression. We really do have our hair stand up a little bit under certain circumstances. And that's because there's a tiny muscle attached to each hair follicle that actually contracts and pulls our hair up. And it does that when we are cold, because if we had real fur, that would actually increase the thickness of the coat, basically give you a thicker coat of insulation and help you retain body heat. Ours doesn't do much that way, but that vestigial reaction remains. An easy way to observe that is, if you have a bird feeder and it's a really, really cold day, you may notice that the birds are all fluffed up. Now, birds are not mammals, but it's the same effect of just, basically thickening the layer of insulation. So that's why it happens when we're cold. The reason why it happens when we are frightened is because if you have had a cat or a dog, they fluff up when they're angry or worried. And the reason for that is partly it makes you look bigger, and it will also obscure the area around your throat. One thing that nature documentaries can sometimes be misleading about is animals really are better off avoiding getting into fights. So fighting may be colorful and make for good TV, but by and large, if animals can avoid getting into fights, they're better off, because a wound in nature might be fatal. So if you can settle your differences without actually having a fight, everybody's better off. So if you can make yourself look bigger, such that your opponent, whether it's a predator or a fellow member of your own species with whom you're having a disagreement, if you can make yourself look bigger and generally convince the opposition that they'd really rather back down, that's a huge benefit. So there are lots of different ways that animals try to make themselves look bigger under various circumstances for various reasons. But in the case of fur, as I said, you get frightened, the hair stands on end, you look a little bigger. It's also going to mean that, if somebody's busy trying to claw you, they're not quite sure where the surface is. It has a bunch of advantages. Doesn't do us any good because our fur is negligible. But there we are. And that's kind of a good example of a vestigial organ. All those little hair muscles, all those little hairs and all the little hair muscles that are attached to them. I mean, seriously, what good does it do us? But it's there, doesn't do us any harm really. And it's kind of a nice reminder that our ancestors were furry.
Is that where goosebumps come from?
That's what goosebumps are. That's exactly right. That's why you get goosebumps when you're frightened and when you're cold. That's the hair standing up on end.
Speaking of animals that puff themselves up, I'd like to talk a little bit about some of the science denial coming from our political leaders. We have to be careful about this because we are forbidden as a charitable organization from endorsing or condemning a political candidate. So, but we can talk about policy issues. And especially as it relates to science, one of the things that has concerned me is a general tendency, and then we can talk about some specifics, but a general tendency of some of our political leaders, or even erstwhile political leaders, candidates and whatnot, to either downplay or downright disregard or contradict scientific findings. And as humanists, one of the things that all of us share is a philosophical position that science is the primary way that we learn about what's real, true, and possible. But not everybody has that same philosophy. And there's no mandate that political leaders have that philosophy too. We see this kind of science, what you might call science denial, especially in the context of global warming or climate change. And it's been very pervasive in discussions and policy decisions about climate change. And frankly, I can understand part of the motivation for that. Changing our way of life, changing the automobiles that we drive means buying new automobiles, means we wouldn't be able to resell our existing automobiles. Changing out our incandescent light bulbs, which has happened over the past decade, has meant spending more money on light bulbs that cost more. And so the economic impacts of changing our way of life can sometimes be painful, especially for people that don't have, enough disposable income that they can suddenly go out and make a big purchase of a new, more efficient, energy efficient car, for example, or change all the light bulbs in their house. So I can understand a political reluctance to implement policies that are consistent with the best scientific knowledge we have. And global warming is one of the examples of that. One of the implications of global warming is that it causes more widespread droughts and drier areas that are already tending to be warm or have warm seasons. And anytime you get drying vegetation, that vegetation becomes more prone to catching fire. Also, warm air near the surface, as the surface air warms up, it tends to create more turbulence, and that warm air will rise and cool off and create storms. So we may get more violent and more frequent storms as the world warms, and those storms might cause lightning, which ignite some of that dry vegetation. So all of these systems are intertwined with the relatively straightforward notion of climate change, everything from increased severity of storms to increased frequency and severity of fires. And I was just wondering, that provides a little bit of background from my perspective on some of the friction between, say, economics and science policy. I was wondering what some of you think about ways that we can do a better job, potentially, of implementing some of the ideas that science have, of making sure that our politicians are better educated and empowered to make better decisions about these kinds of topics. So just sort of an open topic that any of you that have ideas about that.
You note the reluctance to even get into that pit. There are all sorts of snakes and snarly things and everything else just waiting for anyone to step into that.
Yeah.
I think part of the problem is that there can be political advantages to having things go wrong. That if things aren't working out well, that gives certain political coalitions something to appeal to their base. So, so in other words, one of the problems with global warming is that the worst of its effects are probably going to be a few decades away. Not only that, they're sort of delayed. So the whole system has some momentum. So even if we overnight transform our system to be using renewable energy, electric cars, and so on, it still may be decades before we see the deceleration of global warming. So political calculus tends to be very short. People are thinking about, how do I win the campaign that's 2 years away or 4 years away? And it makes it difficult for a politician to, there are a lot of, what should I say, incentive to play a game to get elected in the short term versus address a long-term issue.
And one of the notions that I've had in the past when I've given talks about political science is science as a set of methodologies has built-in feedback loops. So, the classic scientific method sort of formula that you learn in middle school has some problems with it from a philosophical and even a practical standpoint. But as an illustration of some of the methodologies of science, it can be useful. For example, you observe the world, you make a hypothesis about what's happening, you formulate a model or an explanation about why that's happening and how you might change what's happening. If you understand the way the world works and what the mechanism is, you then have some capability potentially to intervene and change the behavior of the system to a more desirable state. So scientists typically observe, make an idea or hypothesis, and then twiddle some knobs or do some experiments and then observe the outcome and see if that outcome corresponds to their expectation about how that twiddling and lever pulling would affect the world or affect the particular system. In my opinion, if we did a better job of implementing that same kind of feedback in political discourse and in political, social, and economic outcomes, that would put us in a better position. Economics has this idea of unintended consequences, where you do something based upon some virtuous idea and it ends up having a really negative impact. One of the classic examples in economics is rent controls. So if you implement rent controls, then the prices of residential property cannot increase the price of renting. Well, that provides a disincentive for builders to construct more property that would be associated with those levels of rents. So rent controls typically are implemented at the modest level or middle class or lower socioeconomic levels, but there's no cap on the rent prices for very expensive abodes. So builders, in order to make a profit, instead of building many inexpensive dwellings, build fewer extravagant dwellings. They can get a better return on their investment for that. So that's just one example of an unintended consequence of a virtuous idea that, well, wouldn't it be nice if we could enact a rule that kept rent prices low so that people wouldn't have financial difficulties. So yeah, go ahead.
I liken this very much to a buffer solution. Again, a good chemist. That is, when you're titrating an acid with a base or vice versa, there can be various plateaus. And during the process of titration, you'll come along and it'll go very, very, very slowly down, 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 and all of a sudden break. And then go along and all of a sudden break again. And this is a basic thing that you see with multiple systems. I think the problem with the planet Earth or any other planet is it's a huge buffer system. There are many, many, many buffers, and they are interacting with each other. So we look at one variable. We can only study that one variable, but it's only one amongst thousands of them that are interacting. And we as scientists sit back there and we build these huge computer programs and everything else and try to come up with some prognostication of the future. And we generally come up with many and say, which trend line do we appear to be following? And again, that's a buffer situation. We really don't know. We can project. We can say all of our projections are going in a specific direction. And so we could say, yes, we are in a position now that the planet is heating. And what would be the consequences of that? Well, we could look back in the history of the planet and say, at other times when the heat has been this high, then certain plants, certain animals, certain things have occurred or haven't occurred, and that the transition is always a difficult one. We see many species going out of existence and other species coming into existence during these transitional periods. And so one of the problems that we run into with trying to explain this to the common person is we don't have a cause and effect.
Or a simple model.
a simple model because it's not simple. It's a hugely complex problem that none of us truly understand. We build these marvelous computer systems and say, here are our trend lines. Here are our 5 basic trend lines that going from very low to very high, and saying, which one of these are we following? The problem that we're seeing is that when we make projections and we look at the low, medium, high, and is that we are progressing beyond our highest expectations. Everything is happening faster than we had ever projected. And if we look at things like what's happening in Antarctica, what's happening in Greenland, to the ice caps,
Yeah.
this is we're 20 to 30 years ahead of our most exhaustive explanations.
The most pessimistic models haven't
Oh
predicted.
yeah. So if it says it's going at this and this, that's our highest one, we're actually doing this. And how do we explain this? Well, in many cases, people say, well, you scientists, you just don't know what you're talking about. If it's supposed to be here and it's here, you don't know what you're talking about. And in fact, that's true. We don't. But we are saying this is a very, very troublesome area. And unless we modify it, no matter which one of our projections is correct, if we don't modify what we're doing right now, we're going off the deep end. That there will be a point at which everything collapses and there's nothing we can do about it. And that's the so-called tipping point.
Right.
And many of us, myself included, believe that we've already gone beyond that tipping point, that there is nothing we can do anymore. And that's an extremely pessimistic point of view, but I got it and it's mine.
Well, the other problem is that let's throw away all those complexities and just look at the simple core idea of the greenhouse effect. It's a subtle thing. It is hard to explain it. It's as physics. It's not easy peasy stuff. You know, why is there tropopause in the first place? How does the altitude of the tropopause control the surface temperature? And you get into molecular weights and ratios of specific heats and radiation transport and yada, yada, yada. And that was, you know, back in my day, advanced undergraduate physics at MIT. Well, how do you explain something that where you really do need the sort of background that an undergraduate physics major at MIT has in their and when they're upperclassmen? You know, it's a hard thing to understand, to explain to people who aren't physicists.
And there are also the businesses of, as you said, of delayed reactions and some things that we weren't quite sure how they were going to turn out, kind of as you said about buffering solutions. I'm thinking back to when I was reading about biogeochemical cycles back in the early 80s. Carbon is but one biogeochemical cycle. But it was talking even then about, you know, the record amounts of carbon dioxide that were being put into the atmosphere, and that this should lead to global warming. But exactly what was going on and what role did the oceans play anyway? Because at the time, there was not as much warming as it might be expected. And it's like what was happening to the CO2. This was back in the early 80s. And the oceans might have something to do with it, we thought at the time. Of course, now we're seeing the acidification of oceans. And that's a byproduct of the same process of pumping CO2 into the atmosphere. But it probably did mean that for a while, at least, we were not seeing as much of a greenhouse effect would have.
So Abby, you know, in Earth's past, the Earth has occasionally been much, much warmer than it is today, and life survived. So why do we need to worry?
There's a difference between life surviving and your life surviving, or your progeny's life surviving. Yeah, life is, you know, pretty adaptable. But evolution, one of the ways that evolution takes place is, of course, through death. Massive deaths sometimes, deaths of not just entire species, but entire clades, entire genera and orders and so on can simply wind up being wiped out and going away to nothing. Um, so yeah, I mean, if we're really concerned about life continuing on Earth, I think it'll probably manage to do that. It might even be that people manage to continue on Earth in small, rather untechnological pockets here and there, and so on. But if you're imagining a nice life for your progeny and people for in generations to come, then you need to be thinking harder about trying to do something about the current situation.
Yeah,
Right?
that
Life will survive. Human beings will probably survive, but that doesn't mean that they will be comfortable and happy.
Yeah, that is a great segue. We got a question from Peter on YouTube. He said that he thinks it's important to demonstrate the personal impact to people who deny the science, and not only the impact on them, but the impact on their children and grandchildren, and then ask the question, is it worth the gamble? And I think, one of my briefly, one of my thoughts about that is people do a really, really poor job of considering the well-being of their grandchildren and great-grandchildren. They often do a moderately poor job of considering the well-being of their own children from a long-term consequence. People tend to make decisions that are fairly selfish and short-term oriented, including politicians, going back to some of our prior discussions. So bouncing out of that trend, I think, requires structural changes to the way that we make decisions. And continuing the thought that I was expressing earlier about structural changes in the way we do governance, putting in some deliberate feedback loops where if you implement a policy, at the same time you specify from a legal standpoint what that policy will be, you should be required to also say how the outcomes of this policy will be measured and what are we measuring against in terms of our expectations. So, assistance for the poor, tax cuts for the rich, environmental changes, whatever the case may be, there's always some kind of philosophical, social, economic motivation for these. And I think that my position is that those should be stated explicitly up front. And then also we should state how we're going to measure the outcome of our policy and when we're going to measure the outcome of our policy to see if it brought about our expected changes. And then finally, provide a mechanism for either aging that law out of the books or requiring a modification if the outcome does not meet the expectations. And that's what I was referring to when I was talking about feedbacks in policy that might emulate some of the feedbacks that we do just by nature as part of the scientific methods.
Well, one thing that is talked about often, and this does not immediately have to do with what you were talking about, because sometimes stating exactly what the consequences will be of a given policy, as you said, are not always known in advance. In many cases, I mean, Roosevelt basically said, try something, see if it works, and if it doesn't, try something else. Right. But one thing that is talked about frequently as a policy way of addressing climate change and specifically putting CO2 into the atmosphere is carbon pricing. And that has the advantage of working with a capitalist system in that that's basically rearranging financial incentives so as to favor putting less carbon into the atmosphere. Capitalists are pretty creative at figuring out how to make money. I mean, that's what they do. And if you make it such that it is expensive to put carbon into the atmosphere, they'll figure out how to not do it. And likewise, if you can figure out ways of doing carbon capture, as I said, if there's money in it, people will figure out how to do it. And so part, in fact, of what policy needs to do is reward the behavior that we want to see. And for something as simple as not putting so much carbon into the atmosphere or removing carbon from the atmosphere, if that is priced in a certain way, as I said, business people are very, very good at figuring out how to make money off of any given set of incentives. And I don't consider this to be an artificial thing to do because we create economic incentives for all kinds of things all the time.
Even imaginary things or things that we've created out of whole cloth, like media, entertainment programming and whatnot.
Right. So, but I mean, but we incentivize or disincentivize things economically all the time. So this would not be particularly a departure from, the way our system works to put a price on carbon.
Yeah, that's part of the, I believe, cap and trade idea that if you're a carbon emitter and you can't get down to a particularly low target as a carbon emitter, then you buy credits from people who've exceeded their carbon targets, et cetera. And that idea that you could create a free market for carbon emission credits, as it were. Really a well thought out program. But again, it gets into the realm of something complicated enough that it's difficult to explain in a soundbite. And a lot of our political leaders really enjoy sound bites. We ought to get Neil deGrasse Tyson on this problem because he's a scientist who is really known for pithy sound bites.
Mm-hmm.
But again, I think this requires an intelligence in the political sphere that we do not see anymore. When I was a kid, the Republican Party in general was considered to be the party of the intellectual. And I don't see either party being the party of the intellectual any longer. I see political parties as being very reactionary and very emotional rather than putting the frontal lobes into action. So although it's a wonderful idea, I don't see it happening.
Yeah.
Well, I mean, it happened to a degree. For instance, I live in Massachusetts, and right now I have solar panels on my roof. And that happened in part because the government came up with this wonderful thing known as a solar renewable energy credit, or SREC for short.
Is that a state credit or federal?
I believe that was a state credit.
Okay.
But what that did was that because suddenly gathering electricity from the sun actually became a valuable commodity, suddenly lots of companies sprang up that wanted to put solar panels on any roof that had enough sun on it. I happen to have a very nice south-facing roof, and we had people calling us up on the phone asking if they could put solar panels on our roof. I actually went through mass saves and did sort of everything in a planned way and had an energy audit done on my house, and they told me some things to do that would make things better. And they gave me some efficient light bulbs, which was very nice. But I also got 3 different mechanisms by which I could get solar panels on my roof. One was essentially renting my roof out, where I did not own the panels in the slightest, but I got slightly cheaper electricity out of the deal. Or you could wind up putting a little bit of money down and getting a much better deal on electricity, or you could buy the panels outright and then you would own the SRECs, the renewable energy credits, which you could then trade on the open market and make money that way. But that would require spending more time dealing in SRECs than I really felt like dealing in. So I did not take that option. But it would have meant that basically if I had no money whatsoever, but I had a roof, I could have gotten solar panels on the roof and it would have benefited me financially, as well as putting solar generated electricity into the power grid. And as you probably know, when it comes to power, getting electricity on a hot summer day, which is when solar panels are at their best, is what you really need, because at that point, hot summer days are usually when you have peak energy demand. And so this was a way of actually providing extra electricity exactly when people need it most. And all of this was done by way of a little bit of government incentives. As I said, those government incentives wound up putting solar panels on my roof, around roofs all over Massachusetts. It kind of jump-started the solar industry here. Now we have one.
Yep, my roof too.
Really?
And you don't exactly think of Massachusetts as being a place with tons of sun,
Right.
like say Arizona or something like that. But nonetheless, you know, it is financially not just feasible, but beneficial to us to have these panels on our roofs.
The amazing thing about silicon technology is that industry is extremely good at making silicon technology cheap. And that's what solar panels are, and that's what the other thing is, that all the infrastructure under the panels to actually turn that energy into usable electricity, all of the optimizers and inverters and all that stuff has gotten extremely cheap and reliable. And in fact, now the dominant cost of installing a solar system is the cost of hiring the people to put it up there. The machinery doesn't cost much, and you put it up there and it lasts for years.
And at this point, that's actually a decent source of jobs.
That's right.
Installations.
Yeah, if you want to keep the industrial economy going, installing renewable energy is a great way to do it.
Yep. Speaking of renewable energy, I don't think we mentioned this in passing one of our recent chats. I can't remember for certain, but did you guys see the news story, guys and gals, about painting one vein or one blade of a windmill black, and that helped significantly reduce the number of birds that were hitting the windmills?
No, I hadn't seen about that. That's really interesting.
Yeah, that's one of the big objections that you hear about windmill power, is that it kills birds, and so this is a way to at least ameliorate some of that damage.
Well, you can also have windmills that frankly turn slowly. And I have also seen windmills. This is something where one of you might know more about what happened to this idea than I do. But at one point I saw, I won't even call it a windmill, but I will call it a wind electric generator that was almost like a double helix. It was a column like this that turned around like so, and it could operate in very low winds. So you could, you know, essentially have them in your backyard. They definitely didn't kill birds, and even a light breeze usually would get them going. And there was one place where I was where that did generate some of the electricity, but I have not seen much about that particular design since then. I'm wondering if any of you know anything about that.
Although I'm aware of it, I haven't seen anyone advertising it. Everyone is going for the windmills, you know, the tri-bladed windmills.
Right, right.
Yeah, there have been a lot of different designs for vertical axis wind turbines. That's what they're known as.
Okay, thanks.
And they just haven't proven as efficient and capable as the three-bladed
blades, right?
you know, the horizontal axis wind turbines.
It's also a matter of scale, right? So the village that I live in Illinois, has some street lights in its downtown area that are powered by those helical wind turbines. And so on top of a light pole, you'll see one of these little helical generators doing its thing. Like you said, even in a mild wind of a day. But one of the things that comes to mind, I'm no expert in this, I haven't looked into it, but just off the top of my head, one of the things is the economies of scale might play a role. You know, putting in the copper wire and building the blades and making these small single purpose windmills. I wonder if it's more efficient to repurpose those permanent magnets and copper coils and whatnot to make a larger device that is more efficient and generates more power. So I don't know about the economies of scale of that, but you know, the fact that we see a lot of these really large windmills makes me think that some economy of scale factors may be playing into that.
Well, the energy density of wind energy is considerably less than the density in sunlight. And so if you have a limited amount of space, it's usually better to put up a solar panel. Now, if you have the wide open spaces of Nebraska, it makes sense to put up wind turbines, but to put something on the top of a streetlight pole, for example, you're going to capture more energy with a solar panel than you are with a wind turbine.
And you do see solar panels on top of streetlights.
Yes, you do.
But one of the things that I enjoy is watching the bicycle races in Europe, and recently, of course, there's been the Tour of France, and it's amazing how many acres of France are taken up with solar panels, and they'll be riding their bicycles down through this forsaken area. You know, there's a beautiful chateau here, and there's a vineyard over there, and then there's this huge area of of solar panels. And it looks to me like this is something which, again, France is taking advantage of, and I would assume that also places like Germany and most of Europe is taking advantage of that, rather than the windmills. For again, space, I think is a huge problem.
Mm-hmm. But all of this is, in a sense, by a way of pointing out that such things are possible. And it really is just a matter of what is encouraged, what incentives are put in place, and so on. Those will be the things that generally happen. I mean, it's not a perfect correlation, but there's a lot of correlation between what is rewarded and what you get.
Yeah, understood. Yeah, and the incentives and before we started our live stream today, right as we were doing it, I forget exactly, but I mentioned the idea of modern monetary theory, the idea that the government can inject money into the economy by paying for goods and services and other mechanisms, as long as there is slack in the economy. And if there's latent demand for things like renewable energy, then the government can help incentivize people like Massachusetts did potentially by giving credits, tax credits, or other incentives or direct payments in some cases for implementing some of these policies. So the linkages between science, between governance, and between economics are very complex, and something that I think we could manage better.
Mm-hmm.
Switching gears again back to physics, a very puzzling question occurred to me the other day, and that is, I do some work with amateur astronomy and amateur astrophotography and whatnot, and one of the things that I remember, and this is evident in rainbows as too, if I remember correctly, is that a prism or a or a lens with a you know how a lens is kind of shaped like a smoothed out prism, two prisms stuck together, or even the internal reflections in a water drop that cause a rainbow. One of the things I remember learning many years ago is that it's actually the higher energy light, the blue light and the violet light, that is refracted more through a prism than the lower energy light. Lower energy light passes through without as much deflection. So I'm wondering, why don't we use prisms or lenses that seem to operate more and more strongly on ever more energetic light to protect us from things like gamma rays and X-rays? Why can't we just use our normal optical devices to extend into the some of the invisible electromagnetic radiation?
Okay, so you want to make an X-ray lens.
Yeah, how do you do that?
Well, it's really hard. The reason that ultraviolet refracts more than uh, visible light in typical glass is because as you approach the energy levels of the outer shell electrons in the material, the refractive index increases as the frequency rises, and using the Planck relation, as the energy rises along with the frequency, the what happens is that you're approaching this situation where you're reaching the energy levels of the outer shell electrons, and you're bumping them around more. Now, when you actually reach the point where you can kick an outer shell electron out of the atom, then everything changes, and instead of refracting light, you're absorbing light.
Oh, I see.
And so glass gets very opaque in the ultraviolet. If you want to do far ultraviolet, you'd make your refractive elements out of fused quartz. If you want to go into the extreme ultraviolet, you have to use reflective elements, because there's just nothing that is a practical refractive material.
So our X-ray telescopes, then, they're reflective and not reflective?
They're reflective. Now, there's an interesting thing that happens in the X-rays. When you get way above this point where you can ionize matter, the atoms, the electrons to the X-ray look like almost free. The outer shell electrons look almost like free electrons as far as the X-ray waves are. And when you have a bunch of free electrons, there's an interesting plasma effect that you get. And that is that the speed of light, as measured by how fast the waves move, is actually faster than the official speed of light. This doesn't violate relativity. It's because while the waves are moving faster than the speed of light, groups of waves are moving slower than the speed of light. And so if you were to look at a clump of waves in a X-ray pulse going through a metal, what you would see is within the pulse, the waves start at the back and they move to the front of the pulse and they die out, and they keep doing this. And the pulse moves slower than light, even though the waves are moving faster than light. Now what happens, let's suppose that you have an X-ray, X-ray waves coming in at grazing incidence to a metal. Well, let's show the waves like this. Well, what happens is when the waves start to penetrate the metal, the parts of the wave that are inside the metal move faster. And what that means is the wavefront bends. And it bends, and so it comes back out again. It's analogous to total internal reflection in glass, if you know about that phenomenon.
Right.
This is called total external refraction, and it's because the speed of the waves in the metal is faster than the speed of the waves in the vacuum outside. And so what we do is we make grazing incidence optics. We run the waves in at very shallow incidence angles and reflect them to whatever we use for detectors. My specialty is making CCD detectors for X-rays.
So does an X-ray telescope then consist of a thin tube, like a straw, like a soda straw of metal, or?
An X-ray telescope. Let's see if I can share my screen.
Oh, that'd be awesome.
Let's see here. Okay. You know what? Let's first get out of, there we go. And now we'll move this window aside and hide that. Where are you? Where's that picture? Oh, come on. I had it. There we are. Okay. Now I need to go back and I need to, never done this before on Zoom. There we go. Desktop 1. Share. Can you see that?
Yes.
Okay. That's an X-ray telescope. That's one kind.
So those are flat surfaces there?
Well, no, you can see that this is identified as a hyperboloid. It's got a slight curvature.
Okay.
And this is identified, oh, I'm sorry, this one's the hyperboloid and this one's the paraboloid.
Okay.
And it turns out that makes a relatively aberration-free image through two grazing incidence reflections at this point. And that's how the Chandra X-ray Observatory works, for example. The Chandra X-ray Observatory has four cylindrical shells that each have a hyperboloid section, or a paraboloid section and a hyperboloid section. You know, there's one on the outside and there's one interior to that and interior to that, and they're all arranged to focus at the same place. And so you have an X-ray telescope. There are other ways. This is what's called a Kirkpatrick-Baez optic. That's used for X-ray microscopy more than for telescopes. The little bit of trivia here is that the Baez of this was the father of the folk singer.
Huh.
He was a physicist. And this involves reflections off mirrors that are perpendicular to each other, but are grazing incidence to the incoming radiation. Then there's another scheme where you just use one reflection, and these mirrors are just paraboloids, and we usually make them as very thin foils, and then we can nest a whole bunch of them. The nicer pulsar observatory on the space station uses, I think it's 28 nested foils to get quite a bit of collecting area from a simple optic. The problem with a single reflection is that you get terrible off-axis aberrations. The images go way bad as you move away from the single point at the center of the focal plane. And so what we use these for generally is when we're looking at point objects like pulsars,
Okay.
where you're never going to resolve the pulsar, so you just focus the X-rays on a particular spot on the focal plane, and you don't even use an imaging detector. You use a photodiode basically. So that's another scheme. See, I've got something else. For hard X-rays, the grazing angles become very so low that they're not practical. But what you can do is that now you can make a multi-layer, and you can get a little reflection off each layer. And if you combine them so that the reflections are in phase, you can get a pretty strong reflection. The New Star Hard X-ray observatory uses a multi-layer mirror of this sort. And then finally, another one that's dear to my heart is the coated aperture, which doesn't focus the X-rays at all.
Huh.
What you do is you make a mask, and the mask has a bunch of holes in it, typically arranged in a pseudo-random pattern, and that stops X-rays in some places and lets them through in others. And so on your detector, you see a pattern of shadows from the mask. And then you use computer techniques. They're similar to what a CT scan uses. Actually, they're closely related to recover an image from this coated aperture. These are particularly nice for very wide fields where you're looking at bright things, but you don't know where they're going to be, like gamma ray bursts. Huh. This is what my HETI 2 mission used back almost 20 years ago now, and this is what the SWIFT mission uses to do gamma ray bursts. So that's another method.
Phenomenal.
Lots of interesting things you can do with X-rays.
Wow, that is just phenomenal. That's really, I'm blown away at how different each of those mechanisms is. The only analogy that comes to mind is the difference between like a Newtonian reflector and an optical refractor for optical astronomy that I deal with. But these different methods, all for just trying to bend little bits of light onto a focal plane, are just really amazing. Thanks for sharing.
Now, the Vulture telescope is closely related to the Cassegrainian.
Okay.
But it's a Cassegrain, it's the Cassegrain math with the restriction that you're only allowed grazing incidents.
Is there like a corrector plate then in the front of this?
No, there is not.
Okay. You
can't do that. You see, that's the problem. We can't do refraction very well. I mean, there are ways, but they don't work very well.
Wow. Fantastic. Well, we're at our hour and a half mark. Unless there's any other questions that any of you have thought of, Dave hasn't alerted me to any other questions from online. So anybody else have any closing topics or questions they'd like to throw out there before we close for today?
A definite wow. Thank you, John.
Well, it's just, I've been doing this for decades, and I have had a lot of fun.
Yeah.
X-ray astronomy and gamma ray astronomy have been fun. But let me brag that I'm a co-author on a paper that came out in Nature last week that had nothing to do with either X-rays or gamma rays.
What did it have to do with?
A planet that we discovered with the TESS observatory, which is a giant planet orbiting a white dwarf star.
Oh, I've seen a news story about that. Yeah.
And well, I'm a co-author on that paper. And the only way we can figure out how it could have got there is that it was swallowed by the star in the red giant phase, and it spiraled in, but it didn't quite make it to the core before the red giant blew its envelope off and became a white dwarf.
Wow.
Huh. So it couldn't, you don't think it's plausible that it could have accreted afterward, for example?
We do not think so. We do not think that's a plausible scenario.
Okay. Fantastic. Well, I've just had so much fun today. I hope our viewers have enjoyed it as well. We'll continue to expand our advertising, and I was notified by Dave that there was a little technical glitch when we first started screen sharing, that we need to alert him before we do that, so that he can make sure that the computer that's doing the broadcasting can accommodate the screen sharing. So we'll give him warning about that in the future. But it's been a great discussion today. Thank you so much, all of you, for joining us. And we'll do this again. Our schedule is that we like to do this on the Saturday before the first Sunday of a month and the Saturday prior to the third Sunday of a month. So we'll be, let's see, let me look at our calendar here.
No, the calendar's not here.
So it looks like the third, so in 2 weeks, in October 3rd, we'll do this again and talk more wonderful, exciting, fun stories from science. Thank you, everybody.
Thank you, everyone. Have a great day. Say hi to Darwin for me
I will.
and Dave.